Arguably, the most significant scientific instrument in history has been the Hubble Space Telescope. It has changed our understanding of the universe, yet it has posed serious new questions about the nature of matter itself. Hubble has confirmed the widespread distribution of black holes and has viewed light from galaxies more distant than anything previously seen. As well as its scientific discoveries are the stunning images. In 1609, Galileo built an early telescope and soon turned it to the night sky. The telescope was a powerful tool that led to a complete re-evaluation of the Earth's place in the universe. In 1668, Newton invented the reflecting telescope to eliminate the problem of uneven refraction of the different wavelengths of light. The reflecting telescope became the design of choice for astronomers, and in 1781, William Herschel used an instrument he had built himself to discover the planet Uranus. The Newtonian telescope was scaled up to immense proportions, and in 1924, it was with the 2.5-meter Hooker telescope at the Mount Wilson Observatory that Edwin Hubble realized the Milky Way was not the universe, but just one of countless galaxies. But there was still a problem. No matter how mathematically perfect a telescope is, its images are distorted by the Earth's atmosphere, and some wavelengths cannot reach the ground. In 1946, astrophysicist Lyman Spitzer proposed a telescope in orbit above the Earth's atmosphere. The idea clearly outstripped the technology of the time. But by 1966, NASA began launching a series of orbiting astronomical observatories. Only 2 were successful, but the telescopes in low Earth orbit were the first to see the night skies in the ultraviolet part of the spectrum. In the 1970s, plans were drawn up for a large orbiting telescope. Part of its brief was for it to be visited regularly by maintenance crews, something that would become possible when the Space Shuttle went into service. The design called for a 2.4-meter primary mirror ground within very fine tolerances because it was required to function well into the ultraviolet spectrum. Originally known as the Large Space Telescope, it was slated for launch in 1979, but delays in construction led to several postponements, and the Challenger disaster led to more delays. In 1983, the name Hubble Space Telescope was adopted in honor of the man who confirmed that the universe was expanding. Finally, in April 1990, Hubble was ready for launch.
Sound suppression water system has started. T-minus 13 seconds. T-minus 10, go for main engine start. We are go for main engine start. T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Hubble has a unique relationship with the Space Shuttle, which would revisit the telescope on 5 different occasions. At this stage, nobody understood just how vital these missions would be. To deploy Hubble, the shuttle Discovery set a new altitude record of more than 600 kilometers. Release of the telescope was routine. It took several weeks methodically checking Hubble's control and communication systems before astronomers working at the Space Telescope Science Institute in Baltimore could see Hubble's first images. Results were disappointing. Images were blurred. The telescope's mirror had been accurately ground, but to the wrong shape. An incorrectly assembled test instrument had been relied upon during manufacture, and nobody had double-checked. Soon a fix was proposed. Because the error was understood, a corrective device could be fitted to the telescope. A series of small mirrors would compensate for the primary mirror's defect. It was called COSTAR, another of those cumbersome NASA acronyms. Training astronauts for the job of accurately installing COSTAR began. The high-speed photometer would be scrapped to make room for it. In addition to correcting the optics, a number of other modifications were set in train. A new wide-field planetary camera would be installed. The original was obsolete. The telescope's solar panels would be replaced. There would be a new electronics processor, extra magnetometers, and 2 gyroscopes would be replaced.
10, 9, and we have a go for main engine start. 5, 4, 3, 2, 1, and we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Finally, in December 1993, the mission to repair Hubble began.
Roger, roll, Endeavour.
It took the Endeavour 3 days to catch up with Hubble, and it was clear from the beginning that one solar panel was damaged. The work on the telescope was considerable, and there were 5 spacewalks scheduled. Firstly, the shuttle's robotic arm grabbed the Hubble so it would remain stable while the work was carried out. The work would be shared between 2 teams of 2 astronauts. Over 5 days, the allocated tasks were carried out, with the Space Telescope Operations Control Center monitoring the Hubble's performance as each new component came online. Most of the parts replaced were stowed in the cargo bay for return to Earth, the one exception being the damaged solar panel, which was set adrift in space. All 5 spacewalks went according to plan, with the only major problem being the difficulty involved in closing the telescope's doors. On the 9th day of the mission, Hubble was released. It would take controllers on the ground another month to fully check the telescope's new systems. Hubble had been repaired in December 1993, yet it would take close to 2 months for technicians on the ground to run through a complex series of optical alignments before they could be certain that the telescope was performing correctly. When astronomers finally saw results, they were stunned at the quality it was delivering. The repair mission had been successful. With the services of a powerful new tool finally at their disposal, astronomers at the Space Telescope Science Institute began addressing a pressing list of demands for time on Hubble. In March 1993, a comet had been discovered orbiting Jupiter. Its path suggested that it had only recently been captured by Jupiter's gravitation and that it would soon crash into the planet. No one had ever seen a collision between bodies within the solar system, and opinions differed about how visible the impact would be. Soon, Hubble captured this image of a chain of fragments. Comet Shoemaker-Levy 9 had been shattered by Jupiter's gravitation. The fragments ranged in size from several hundred meters to several kilometers across. Over 6 days in July 1994, Hubble observed the pieces crash into Jupiter's unlit face. As the planet revolved, the impact region showed a series of black swirls. Some of the dark shadows were as large as the Earth, and they persisted in Jupiter's atmosphere for months. Spectral analysis from Hubble revealed diatomic sulfur and carbon disulfide. These had never been seen at Jupiter, yet the amounts detected were too great to have come in with the comet. They had been stirred up from the planet's interior. Scientists learnt so much from observing these impacts, yet the observations almost didn't happen. Just days before the first impact was due, Hubble began acting unpredictably and then went into safe mode. It would not execute any of its instructions. Technicians suspected a memory problem and took measures to switch across to new memory installed on the recent service mission. Things started to improve until the spacecraft reported it had entered zero gyro sum point. It appeared that 2 gyroscopes had failed and the situation had dramatically deteriorated. The problem was traced to a counter that had run out of numbers with which to count. The issue was understood and quickly resolved. The incident underlined just how complex the operations of the Hubble would be, and that the ground engineers still had to learn how to operate the new hardware. Though Hubble functions as a telescope, it is also a spacecraft that must be controlled with exquisite accuracy. Unlike other spacecraft, it has no thrusters. Chemical residue from rocket engines would quickly contaminate the precision optics. To enable it to move, Hubble has 4 reaction control wheels. As they spin, the telescope will rotate in the opposite direction. Each one has a mass of 45 kilograms, and they are controlled by the telescope's computer. Combinations of spin in any 3 wheels will allow the telescope to point accurately in any direction. They are mounted in angled pairs around Hubble's center of gravity. In 1997, on the Space Telescope's second servicing mission, one of the reaction control wheels was replaced. It had developed an electrical fault. So that Hubble can remain pointed accurately, 3 fine guidance sensors positioned toward the back of the telescope will lock onto any of a series of bright guide stars. Hubble only needs 2 guidance sensors to point with accuracy. They are so sensitive, they can detect wobble in the motion of closer stars. The third vital aspect of the telescope's pointing system is its ability to detect the rate and direction of its movement. Hubble is equipped with 6 gyroscopes that register its orientation. These are essential when pointing the telescope in a new direction. The gyros spin at 19,200 RPM and they do wear out. This is why there are 6 units, even though when designed, Hubble only needed 3 to function properly. With new algorithms, Hubble can now point with only 2 gyros, though less accurately. Work has been done to enable it to work at reduced capacity with only 1 gyroscope. Hubble can point with an accuracy better than 2/1,000,000th of 1 degree. This ability to stay fixed on one narrow region of the sky for a very long time led astronomers to perform a unique observation. For 10 days in 1995, they pointed Hubble at a small, empty region of the sky near the constellation Ursa Major. To some, this was folly, a waste of valuable observation time. The results astounded everyone. This empty part of the sky was packed with irregular-shaped galaxies. Some were as old as 13 billion years. Hubble had looked back in time at the formation of new galaxies in a range of shapes not seen closer to our own Milky Way. It became known as the Deep Field Survey. It was the first of a series of similar explorations of areas of the sky in which nothing had previously been seen. Animators have added depth to these images by using spectral information known as redshift, which indicates a body's distance from Earth. This was a completely new area of astronomy, and it was one reason why Hubble had been built. but the Space Telescope was already running into design constraints. Engineers began work on equipment that would upgrade the telescope's performance in the near-infrared part of the spectrum. This would be fitted during the next servicing mission, along with updated support equipment such as a solid-state recorder, which would replace the original reel-to-reel recorder. Yet even at this early stage of Hubble's life, astronomers were realizing its limitations. The distant galaxies it had seen were approaching the extent of its view in the infrared end of the spectrum. Even with enhancements, the telescope could not be kept cold enough to observe the large redshift wavelengths revealing very old, very distant objects. Plans were drawn up for a new, larger telescope, known as the Next Generation Space Telescope, that could explore the most distant parts of the universe. But there was still plenty that Hubble could do better than any other telescope, and there appeared no reason that it wouldn't continue being refitted with the latest technology as it became available. Early in 1997, the Space Shuttle Discovery visited Hubble for a second servicing mission. Astronauts fitted new instruments to improve its reach into the infrared. In 1999, Discovery again visited Hubble. This mission had been brought forward as 4 of the gyroscopes had failed and the telescope had gone into safe mode.
4, 3, 2, 1, and liftoff of Space Shuttle Columbia to broaden our view of the universe through the Hubble Space Telescope.
In 2002, Columbia lifted off with a new instrument, the Advanced Camera for Surveys. It would replace the Faint Object Camera, the last of Hubble's original instruments. When it departed, Hubble was again in peak condition. Less than a year later, at the close of its next mission, Columbia burnt up during re-entry. Foam insulation had come loose during launch, damaging thermal protection tiles. After an exhaustive search for debris and a thorough inquiry, it was decided that the shuttle system was aging. It would be retired upon completion of the International Space Station. All other missions were ruled out. For the Hubble Space Telescope, this was a death sentence. In the corridors of power, Hubble had friends. The sheer beauty of images from the telescope gave it a public profile, and key senators began campaigning for one last servicing mission. After a new administrator took charge at NASA, a final shuttle flight to Hubble was reinstated. Work began on what would amount to a rebuild of Hubble's operational systems, as well as another update of scientific instruments. New fine guidance sensors would be fitted. All gyroscopes would be replaced, and a new set of batteries would replace the originals that Hubble was still using. Within the imaging spectrograph, a power supply had failed, and training began to open up the unit and replace an electronics board. The Advanced Camera for Surveys had also malfunctioned, and its repair work was seen as even more detailed. Because the shuttle now had to operate with a backup, and because Atlantis could not reach the International Space Station from Hubble's orbit, the shuttle Endeavour was prepared for a rescue mission. On the 11th of May 2009, Atlantis sat on NASA's Pad 39A ready for Hubble's final servicing mission. This was to be the most complex servicing mission. It had to deliver the longest possible life for the orbiting telescope. The 14-day operation went according to plan. When problems arose, they were solved, and Hubble was eventually released as the best telescope it had ever been. On the ground, astronomers from the Space Telescope Science Institute waited for the first pictures from Hubble's new, more sensitive instruments. This means the telescope can operate more efficiently, needing less observing time than earlier incarnations. The team was quick to release examples of the new generation images. In the Eagle Nebula, the pillars of creation, thousands of light years from Earth, immense clouds of hydrogen and dust are giving birth to new stars. The 5 galaxies of Stephan's quintet in the Pegasus constellation. 4 of these are colliding. 16,000 light years from Earth, Omega Centauri in the constellation Centaurus is a globular cluster. Stars here are so densely packed that on average there is just 1/10 of a light year between them. While Hubble has been adding to its list of discoveries, everyone understands that without further servicing, the telescope will eventually die. That slow death has already started, and it's the gyroscopes that are failing. Engineers have been careful, operating just 3 gyros, keeping the other 3 as spares. By mid-2018, 3 of the units had ceased functioning. As the last of the 3 gyroscopes held in reserve was brought online, it misbehaved, and all science operations of the telescope were suspended. By recycling power to the unit, a measure akin to switching it off and back on, normal function resumed. As further gyros fail, the telescope will use its star trackers to help it point accurately. Hubble is expected to function well into the 2020s, by which time a new space telescope should be in orbit. The next generation space telescope is now called the James Webb Space Telescope, named after NASA's Apollo-era administrator. The telescope has been completed and is undergoing exhaustive checks before it is launched. It has a giant mirror of 18 hexagonal segments that is folded before deployment. Compared with Hubble, it is huge, yet the complete spacecraft weighs considerably less than Hubble. NASA built the Webb telescope in collaboration with the European and Canadian space agencies, and it will launch on an Ariane 5 from the European spaceport in Kourou, French Guiana. It will orbit at the second Sun-Earth Lagrangian point, a place 1.5 million kilometers from the night side of the Earth, where the telescope can maintain a stable position. A large, very thin sun shield will protect the James Webb, allowing the optical components of the telescope to cool to around 50 degrees Kelvin. Its operational temperature must be very low to allow it to see deep into the infrared end of the spectrum. The mid-infrared instrument needs to be colder still. A cooler using helium as its refrigerant will enable the sensor to function at just 7 degrees Kelvin. The Webb Space Telescope is designed to build on the work of Hubble by seeing further back to the earliest emergence of galaxies, stars, and exoplanets.